This meeting is being recorded.
Okay, welcome to both seminar. Our today's speaker is Petr, who will speak about set-based generation of optimal circuits.
Okay, thank you, and thank you for inviting me for this talk. Okay, so I'll just shortly, quite shortly, introduce, well, one of my recent works, and actually on and basically there is no big novelty in it, actually. Yeah, only well. Well, this topic has been revamped because you will see why. So right now, okay, I will start with circuits. So what does it mean? A circuit physical implementation of a Boolean function. Yeah. So as a result, we get the network of gates. So I will be speaking about one particular implementation in this talk. The second, say, topic of this is optimal, because they are, okay, naturally, the optimal is the best possible. The question is, what is the best? Because there are, well, really many possible of those bests. Yeah? So it could be the area, it could be delay, it could be power consumption, and sometimes they are contradictory. Okay, if it is, if you have higher area, probably you will have higher power consumption, but it's not the case of delay, as you know. So the bigger, actually, you can design a circuit which is very very fast but very big. Just a case is a two-level implementation, a true stable, basically. Yeah? So exponential size, but on the other hand, it's fast. Okay, so the question is how to design the optimization criterion. So I'm trying. I will try to introduce some ways of introducing those optimization criteria and making them flexible enough. So what's the motivation? Okay, so first of all, from the theoretical point of view, designing the optimal implementation of a Boolean function is it's a difficult problem. It's pretty hard, and in particular, it's been proven that it is in polynomial hierarchy. It's sigmatically complete. Yeah? Well, that reference in that reference you will find a proof that the finding the minimum SOP basically is sigma 2 complete, but it holds in general. So general multi-level circuits then holds. I'm aware of one publication, but I can't lost it somehow. I don't know why. So as a result, this problem is solvable for functions up to just a few inputs, let's say 4, 5, 6, like that. Yeah, we will see that, well, it needs not be the case nowadays. Okay, where is it needed? So first of all, of course, in theory. Basically, by proving that the given function can be implemented by such a limited number of gates, you can prove the circuit complexity. So theoretical bounds. Of course, for benchmarking, you have the lower bounds, the optimal. And so I'm not going to speak about these because it's quite these cases are quite clear. So I will throughout these slides I will introduce one example from. one practical example, which is used in logic synthesis in optimization of bigger networks. Okay, and that's in particular rewriting. Okay, so the related work. I said that work actually the idea or the concept is not new. That's definitely not new. The problem is started from the advent of logic synthesis. So that means so the first often circuits were based on bridge and bound, integer linear programming. Well, surprisingly enough, there was a big gap of say 20 years, and again, new papers emerged quite okay in a sequence of 10 years, and then again a 10-year gap, and nowadays people are okay. I'm 2017, so I say nowadays. Well, actually, to be honest, I haven't seen any papers about it since that time because, well, actually, they have the groups. These two groups have resolved everything at those times. Yeah? So the basic ideas were presented at those times. So one of them was based on SAT, and the second one on SAT. Say I'm going to say some words about it later on. Okay, so why this problem has been studied recently as well, and why I did study the problem was, say, just because of emerging technologies. So there was a need to design optimum circuits which are consistent of gates, gates of some weird types. I can speak a little bit more, but it's a little bit outside of this. So it's just one application of the idea. Okay. So that's why, yeah. The second reason for, maybe the first one, for the renewed interest is that we have very efficient SAT solvers and very efficient SMP solvers right now, especially the SAT solvers, especially so-called circuit solvers, because those instances coming from designing circuits are somehow special. They are not that difficult. So we know that the most complicated SAT has the ratio of clauses divided by variables 4.3. This is not the case. It's more like a two SAT. Yeah? So these instances are very simple to be solved, but of course there are cases, especially when there are XOR gates. So with XOR gates, it's quite a problem sometimes. But there are techniques that can cope with that. Okay, so what I said before, new areas of application. So emerging technologies like some technologies where the circuit composed of majority gates, which are quite cheap, or XOR gates are becoming quite cheap as well. Again, different technologies. And okay, and that's the applicability in a real practice. And most of people who are trying to use those emerging technologies are starting with those with that rewriting because that's the simplest and most efficient process in logic synthesis. So okay, I'll skip this outline. Basically, I right now I'll try to introduce the principles of the rewriting algorithm. The principles are very simple, but first, before introducing the algorithm, just some notation. We have in logic synthesis one of the say really well established structures are so-called and inverter graphs, AIGs, and inverter graph, which are cyclic graphs, and they are composed of just two input AND nodes, and the edges might be negated. So that's indicated by those dashed lines. Okay. Well, Together with my PhD student, the student Ivo Halecek, who unfortunately probably is going to terminate right now unsuccessfully, unfortunately, because of work, a typical case. But he did a big job, a really great job. So especially that's what he did several years ago, and that was extended those INGs to we call it X-INGs. That means INGs with XOR gates. That means we have AND gates and XOR gates. Those XOR gates are identified this by this accident. Okay. And the principle of rewriting consists of taking a part of the AIG and substitute that with its optimum implementation. That's where the optimum implementation makes sense, or use the optimum implementation makes sense. So in this case, it's very simple. So if you take a thorough look at the encircled circuit, so you will find that it is an XOR gate. So this one multiplied by this one negated, plus, that is plus, yeah, when you are using the Morgan rules, negated, and this one negated multiplied by this one negated. So it's an XOR gate. Yeah? So you can simply substitute it by that. So that's rewriting. A more complex case, let's wait. Hardly visible here, so I'm sorry for that.
Could you enlarge it?
Enlarge it? That's true. Sorry. It didn't help too much, but I'll try. Thank you for that. Sorry, I'm quite tired, so too much work. So that's a bit better case where a complex circuit, which unfortunately, or maybe fortunately, you can't you can't see what the function is when just looking at it. But by rewriting, you are able to find that this structure can be two gates only. So how does it work? How the rewriting works? So very briefly, how the rewriting algorithm works. So you iteratively conduct this process. So you extract a k input, so-called cut. That means kind of which has a limited number of inputs. That's important. So the number of inputs is limited, typically to 4. Such cuts are looked up in a list, and then they are mapped to something which is canonical, just by performing simulation. So if it has 4 inputs, so then you can easily simulate it because you have 16 vectors to simulate only. Yeah? So you just transform it to a canonical representation, typically a sum of products, or as I say, a truth table. And this truth, for each entry in the truth table, you have a record where there is its optimum implementation in AIG. So you find the optimum implementation and substitute the cut with the optimum implementation. That's it. Yeah. So that's the principle. That's the principle how it works. in very simple words, I will try to comment on this a little bit more. So this process is repeated until you can't get any further improvement. Yeah? Okay. So what are the aspects that could be important for us? Well, so we should use optimum replacement circuits, of course. And again, the question is, what is optimum? Well, the practice has shown that, well, having only one optimum structure is not enough. So you can easily imagine that for a given function, there could be several optimum implementations. Different in their structure. Several optimum implementation means having, for example, even imagine an XOR, a simple XOR gate. So implementations, two different implementations with completely different structures, but with 3 gates only. A prime times B prime plus a B negated, or a prime B a prime without negation. Negation in IIG is for free. Okay, so in rewriting, it's been found that it could be, or not could be, it is very beneficial to have all optimum structures, or at least to try several. So not all one should be generated, all should be generated, the maximum we are able to. So we come from, say, from constructive optimism problem to an enumeration problem. Yeah? And moreover, when there is more issue, and that is at the end, then some function should be introduced. And again, obtaining the optimum is not the only having optimum with the minimum number of minimum number of gates, but the overall size should be the main, should be. So and then again, we should have some means to customize the code. So, any questions until now? Everything clear? Okay. So I'll go back to what I wanted to speak about, and so the main part is the how do we generate those optimum structures, and how do we convert that sigma to complete problem to basically NP complete only, and that's simple. Well. The trick is simple, and probably you know several other examples where such a trick is used. And well, and basically, we have an exponential instance size. So from an instance which is polynomial in the original specification, so in the original sigma complete, which was polynomial, now it becomes exponential. Then such an exponential sized instance is solved by sum. Yeah? So again, the second exponential. So basically, as a result, it's exponential both in size and time. Yeah? Okay, how it works. So the trick is that, okay, we want to construct the optimum AIG. How to do that will be presented on the following slides. So for now, I will say we just convert the IIG structure to plus some function conditions to SAT instance, so CNF. And we ask a question for a given n input function. So remember, try to remember that for some time. N is the number of inputs. I will be using this later on, so that's why it's important. So given an input function, does there exist an it's probably wrong. Actually, it should be sorry, it should be m here. So for an M input function, does there exist an N node implementation? So we start with N equal to 0. So basically, this question could be asked. You can ask the SAT solver if it exists or not, yes or no. Yeah? And we start with N0. That means, can we implement such a function without any gates? Sounds strange, but why not? Constants, for example. Yeah? Okay, if not, okay, we increase N. Then, can we implement it one gate? Again, if yes, okay, we have a solution. And if not, we proceed, gradually increase N. Okay? There could be one question now, if it wouldn't be better to use a kind of byte search, for example. Okay, you don't ask such a question, makes no sense, of course. The reason is simple. The reason is because when you increase N, the instance size grows exponentially. So it's better to start with the simplest ones, even though it is quite a waste of time. Of course, if you know some kind of some lower bounds, so you can start with the lower bound, of course, but still gradually increase it. Okay, how is it done? So how can we convert the IAG, the inverted graph? That's one of the possible solutions. There has been proposed different solutions to this problem. I will mention some briefly. So this is my solution, and it's, from my point of view, that's the best one for explaining, because it's very difficult, very complicated, but simple at the same time. Simple for understanding that, more difficult for implementing. Okay, so how does it work? Imagine an inverted graph, just a piece of it, and those circles represent those AND gates. So circle is an AND gate, and then there are some variables introduced which basically mean, first of all, a connection and a possible negation. So in AIG, I said that an edge could be possibly negated. So that's the case. So basically, we have a K, it's a circuit. So in this slide, this should be K, sorry, not M, not N, but K, sorry, my mistake. So K is the number of circuit inputs, so primary inputs. N is the number of nodes. And now we say, we try to describe the structure of the IAG. So describe such a piece of graph. So what can we say? Okay, for example, we should introduce those negations. So we may say, okay, if this variable is set to 1, by the way, all those variables are binary. That's also why, well, the implementation, or what makes the implementation a little bit more complicated. Yeah, if it wouldn't be binary, it could be more. It would be simpler to implement. But for SAT, it must be binary. So we say, if this variable is equal to 1, so then the M input of the ith node is negated. For example, the connection. So to describe what is connected to what node in an inverted graph. So that means the information that the node I is somehow connected to the node J by that C. So if that Cij 0 means to the left is equal to 1, we say left is basically is a left parent of J. Yeah? Okay. And at the end, we may say that the output, the very output of the IIG is, and of course we have a multi-output IIG. So for all outputs, we can. In this case, there is only one. So that's it. So these are basically some rules, some variables that describe that are needed for the description of the structure. Then we have variables. We need to introduce again binary variables, which basically describe the function. So first we need to describe the structure, and then the function. I don't know what is more important. It comes hand in hand, of course. So what does it mean? Very simply, how it works. We must say somehow that the negation negates, that the AND gate performs AND. Yeah? It hasn't been reflected. Such information hasn't been reflected in the structure. So that's what we do here. Yeah? So we need to introduce variables which saying or describing the outputs, describing the inputs of the outputs and inputs of each node. Okay, some temporary variables like the function after negation, and again basically a temporary one, a kind of negated output. So these are variables, and having those variables, we can construct the clauses. I'm not going to go into details, of course. So if you were interested, I can give you my paper where everything is described in detail. So just to give you an example how it works. So some rules or for functioning must be introduced. That means in order to describe the structure, we must say, well, for example, each node is node input is connected to a node with a smaller index. Why it should be done? Yeah, it will be to solve it. Yeah? Okay, the same with the output. The same for each. Why not again? Additional constraints, but otherwise you would obtain when solving that you would obtain two equal solutions basically because the left one and right. Okay. This could be probably understood the best. Each node input has only one source. Such constraints, there are many of them. So you formulate specifically. Okay, I'm just these are formed to CNN in a straightforward way. And the same about the function. So negated edges. It means if that's quite clear. If given input is should be negated, so the result is XOR with that negation means negation, right? Yeah. So again, that's the most clear, the clearest one. Interconnection again. So if an input is connected to some output, then the values are the same. So that must be implemented as an equivalence. Quite complex actually. The simplest example is really the most difficult one to implement because the equivalence is quite large in the CNF. Output negation the same. Implementing the AND and the network function, and that's one of the crucial parts. And that means how the function works, how the network works. So we have inputs and the outputs. And we have to try out all inputs. And that is what makes the instance having the instance exponential size. Because we do that for each minterm, each out of makes that exponential. So basically the idea is we evaluate the network in this way, that we present all possible minterms to the input and say, and the output must be like this. And that's it. Yeah? So, well, it was the basic idea. So if you went to that, everything was about AND gates only. Right now, we can extend it to XOR gates. Very simply, we introduced some additional structure variables, like saying that the gate is not about XOR, the clauses describing the XOR function. We can customize the XOR case and now complicate it. And basically, if you want to introduce from SAT to PBO to the Boolean optimization, but basically it's also solved by SAT. That's true inside. But from outside, it's better to use it. Yeah. Okay, so we can basically find any cost of each and or. So that's the overall algorithm. I'm not sure if, well, actually, yeah, it could be interesting for you because, okay, in the previous one, there was only one possibility for having the optimum. The optimum was the minimum number of gates. So we started with generating, well, the solution with 0 gates, 1 gate, 2 gates, and so on and so on. Now, you can, let's imagine the XOR, the cost of the XOR gate is, say, higher than that of the AND gate. And we have different costs. And the optimum needs not, or the optimum in terms of the number of gates needs not be the optimum in terms of the size, because the XOR gate is bigger. So how to solve it? So I have proposed a simple algorithm that first find the initial solution with the minimum n, so with the minimum number of gates first, and then we try to increase that n. So try to find, or try to ask a question, and does there exist a solution with n1 gates, which is smaller in terms of size, not of the number of gates. And if yes, so we increase that bound and increase that bound and so on, and if optimum in size. Okay, so some of the next features, so generation of all optimum implementation should be used. So enumeration SAT, probably you know how it is accomplished in practice. You just, after solving the SAT problem, you just add a blocking, so-called blocking clause to the CNF of the SAT, and then solve it again. And by the blocking clause, you prevent generating the same until unsatisfiable solution is or unsatisfiable. Unsatisfiability. And also, well, I did it by a very straightforward approach, just selected. This is being done in a different way. So just to give you an example, or straightforward, there could be different in such a function, and there are 3 implementations of it. These are only AND gates. These are 2 XOR gates. This one, even though all of them. Okay, accomplished for small functions only. Well, so this for k, so k is the number of inputs, and n is the number of nodes. Okay, so as I said, the SAT instance is exponential. The size is exponential with k, with the number of inputs, and somehow polynomial with the number of nodes. Polynomial probably it's like quadratic, but it's good to state it analytically, but something like quadratic. So we are able to solve, say, even instances with or generate optimum functions up to unbelievable 12. And of course, we got quite a lot, but it's been solved. It's like something like two days, or I think so. Yeah, 2 days. You have computed it. Okay, so I have computed into that instance in 2 days. Yes. So it grows, but still we are able to solve that. But not in general. Not in general. If the functions are really nasty, if they are really bad, that means typically they contain many XOR gates. So they never finish, even for much smaller. So in practice, we are somewhere here for about 4, 5 to 6 variables, no more. Okay, what are alternatives and extensions of these different circuit encodings? So in literature, you will find something which is completely different from my approach. Again, it's just different. I can't say if it is better or not. I just went my way, and the others went a different way. Actually, we did the research at exactly the same time with EPFL in Lausanne, who did the same job, but again, we weren't aware of each other, and basically did the same job with different aims by different ways. Strange. Well, there's been let me say, an attempt to use SMT instead of SAT. As I said, are you ever SMT, all of you? If not, no. Okay, sorry, I'm really sorry for that. Satisfiable module theory is that's the abbreviation. It's a kind of extension of SAT, and that means that basically it's like SAT, but you can have, for example, any data types. You can use integers. You can use even floats in there. Yeah. Basically, the advantage of all that is that, well, the instance could be described very easily. So instead of having binary variables, I can have integer variables, and everything will go more smoothly, and the equations wouldn't be that weird. But the result, that must be translated to SAT as well, inside of the SMT solver. How is the most popular one called? Z1. So if you enter into Google Z1 SMT, you will find it. You can learn about it. And so basically, yes, it works. It produces by SMT. They produce simple instances, and probably the idea has been abandoned because they have found that, well, it is not worth the, I can't say effort, the non-effort. It's because the burden imposed by the SMT solver was too much or excessive, and the authors have, after all, they have returned back to SAT. Okay. Okay, another extensions to timing aspects. So timing information is a part of the instance, and the delay optimum circuits are generated in a different ways by solving the SAT problem. And what I also did was a support of so-called polymorphic circuits. That means, for example, if you hit them, they perform a different function. Quite strange. They started with that research in NASA. Okay, but it would be for another talk. Yeah. In NASA JPL, Jet Propulsion Laboratory. And for example, the original intention was to change the function of a rocket nozzle when it heats up too much, for example. But nowadays we have different applications for that. For example, so-called ambipolar transistors, which could be implemented by novel technologies, and they can be influenced by some external signals. So that's the job I did for those guys from they are from Brno, from also Faculty of Information Technology in Brno. Okay, so that's it, and that's all. So I hope it wasn't too boring. Did you understand the ideas? So I have no idea if how much you are aware of these things. So definitely, I'm sure you know what SAT is. So that was why I targeted that seminar to that. And so now I try to introduce or try to make you familiar with.
So the overall idea in rewriting.
Exactly. Well, that's one option. That's one option now, typically because the SAT solvers are really fast. Formerly, it wasn't the case. Formerly, it was actually the optimal structures were pre-generated offline, then stored in one big file, and then withdrawn in the rewriting process from that big file. That's also what we did with my PhD student. And well, it had something, okay, in orders of megabytes, not much. Yeah, but still, that's the fastest way. So in order to enumerate, say, for functions up to four variables, it pays off. So you can generate all implementations of all, say, 4 input functions in a reasonable time, and the resulting size is very is reasonable, as I said, megabytes. Yeah. If you move to 5 input functions, it's not feasible anymore. It wouldn't be gigabytes; it would be bytes maybe, and probably well, more than the age of universe time of computation time. Yeah? So it's completely infeasible. Yeah? So in these cases, well, they are using SAT solvers online during the rewriting process. Yes. Yeah. Just to compute the optimal implementation for the given structure. Yes.
And rewriting code is some kind of local search.
It's a local search, yes. It's just a local search. No worry. All those algorithms are local. Because again, global search algorithms are abandoned many years ago because everything is local.
Any further questions?
Yes.
I have some clarification question basically. So in the when you were designing the writing AIG as SAT, there is no branching factor bound for SAT. Or since you have for AIG, you said the input and has only two inputs, right?
Yes.
But when you're writing it in SAT, there is no bound on the number of inputs you can have.
Basically, again, a good question. And I have an answer for that. People have considered multi-input gates. A clear example has been shown somewhere, not shown, but mentioned, probably in the motivation and somewhere. Doesn't matter. Where majority gates were used. The majority gates have 3 inputs. So basically, you are right. There is no limitation for the number of inputs. So if you decide having a possibility of 3 input and then you can have.
AIG as SAT, like for the SAT algorithm, then having multiple input as that. Make the line different, like would it be useful to use this?
The idea will be the same. You will just find optimal implementation with an. You will just substitute it with the optimum, or you will find like, the principle will be the same, substitute it with the optimum, with its optimum implementation, possibly having 3 input gates. Why not? There is no principle. Well, there has been studies about that, and exactly what gate it was, but they have found that the kind of one of the possible 3 input gates has been found very efficient for implementing functions. But it's difficult to realize to implement it in practice in hardware. So it's just a theoretical aspect. But it's been, people have tried to do that actually. Yeah.
And I had another question about the last constraint that you mentioned for this SAT-based algorithm. When you talk about the inputs, so you have k variables, so this comes as a cost in time, or you have to, does it come as a cost in space? Do you, each of these mean terms, do you have to embed them in the circuit, or you do it one by one? How is it done? I'm not very familiar with it.
Basically, you know, that's not, as you say, embedded in a circuit. It's something we call a conceptual hardware, or you generated a SAT instance of it, are not physically in the circuit. From the circuit structure and from the circuit function, you generate such CNFs, basically. Yes, this is the style. So from there, you have to include a CN, say, these are clauses. Yes, that's true. So basically, you have to include an exponential number of clauses to the SAT instance you are solving for each minterm. Yeah.
But you're doing all the tests at the same time, models,
And
like you're testing the circuit on all possible inputs.
At the same time. So
Yes.
it is basically not an extra interval of time, but of the series.
It's part of the sub instance that you somehow.
so basically, you encode in the SAT instance, you encode the structure, you encode the function, and then you ask, does it exist? Yeah? Does such a structure of such a function exist? And if the answer is yes, so then the evaluation or the values of these variables, these and these, mostly these, will say this is the structure which it holds, where it works. Yeah? That's the idea.
I had one more question.
Oh, sure.
So when you say optimum, so basically when you is it like optimum in, are there analytical bounds known for this optimum? Like what it's like after this, when you have this algorithm,
This one, yes,
yeah.
okay.
So this is this 1-2 step. This this is an optimum, but is it optimum? Like is it a heuristic to find an optimum, or are there some theoretical guarantees?
It will definitely find the optimum.
Oh, it does.
It does. By this way, it does find the optimum. Yeah. So you first find the initial solution with minimum n, with the minimum number of gates overall, and it needs not be the optimum in terms of size, because some gates could be bigger. And if you try to increase the size slightly, increase the number of gates, and you will find that the size is smaller. So that means, well, okay, there is something wrong. So let's increase it, and then it could happen that you will find a cheaper implementation having more gates. So that's what happens here. Yeah? You gradually, from the minimum in terms of the number of gates, you try to increase the number of gates, and now we are looking the minimum regarding the cost. And because we increase the number of gates, so we are basically approaching the optimum from both sides. So you will definitely find it. It cannot be better, it cannot be worse. Okay.
Any further questions? No, then let's thank again.
Okay. Thank you. Okay then.